Okay, well, let's get started. So thank you all for coming. My name is Robert Aboukhalil, and I work at Cold Spring Harbor Laboratory in New York. And most of my work focuses on applying data science to large biological data sets. And what I want to do today is actually show you an example of how to do that on the command line with bash. And specifically what we're going to cover is I'm going to start with a brief overview of what is bash, how does it work, what are the most important commands that you need to know to work your way around the command line. And then I'll take you on two adventures where we'll start with a question and answer it using publicly available data sets and bash. And so the first one we're going to answer is, over the last 100 years or so, which day was the warmest in Orem, Utah? Then we're going to tackle another adventure that I think a lot of us have had this question before, which is how often are flights actually on time to their destination? And again, we'll answer that with bash as well. And I'll end very briefly with a few thoughts on where to go from there if you want to learn more about bash and data science. Also, the slides are available at robertaboukhalil.com/talks. So let's get started. What is bash? Well, bash is basically a window. It's an interface that allows you to enter commands, and your computer will process these commands. And it can be anything as simple as creating a folder, deleting a file, or it could be something more interesting for us today, such as going through a file and only outputting the lines that matter to us. Or it could be something like extracting just one column out of a file. Why is bash really useful for data science? In my experience, bash is really nice when you're doing quick and dirty data exploration. It's extremely useful when you're dealing with data sets that are in text format that you need to filter or reshape. And in my work, I use R, I use Python, but oftentimes I also use the command line in bash because it's so powerful. So why don't we get started? When I open the command line, what you will see is slightly different depending on the OS, but in my case, I see my username, so Robert, and I see the current folder that I'm in. And so in my case, it's in between the colon and the $sign, and it's telling me that I'm in the folder tilde, which is just a placeholder for my user folder. And depending on which OS you have, it'll be different. So I'm on a Mac, so it's going to be /users/Robert. But if I was on Linux, it would be /home/Robert. And the first thing we're going to do is actually check what that is. And the command pwd, print working directory, allows you to do just that. It'll say, I am currently in the folder /users/Robert. Okay, great. Now, why don't we check out what is in that folder? There's a command called ls that will list all the files and all the folders that are in the current folder. And just to convey the similarities between the command line and the graphical interface, if I just move this up for a second and open my graphical user interface, you can see that I see pretty much the same things being listed on the command line and on the user interface, except for files and folders that the operating system uses and doesn't want you to really mess around with. So in the graphical interface, it won't show those. Of course, you can access them with the command line. Okay, so now we know where we are in the command line, and we know how to list files and folders that are in a folder. Why don't we move into the desktop and create a folder there, and we'll store all the results of our analyses there. And so to move into the desktop folder, we use the cd command, which stands for change directory, and we followed by the name of the directory you want to move into. And as you can see, I'm now in the folder /desktop. And we can verify that using the pwd command. Okay, and now we want to do something really exciting. We're going to create a new folder using the make directory command, which will just create a subfolder. And we can then move into that subfolder using cd or change directory. Okay, so these are very basic commands that you need to know to just move around in the command line freely. And with that, let's get started with our first adventure. So we want to answer the question over the last 100 years, which day was the warmest in Orem, Utah? And to do that, we can go to the NOAA's website, which keeps track of such data. And it actually allows you to enter a city anywhere in the US, and it will give you information about how much rainfall there was, how much wind gust, tells you about humidity, and also tells us about temperature in our case. And so when I clicked through this interface, it told me that about a weather station that was near Orem, Utah, and I downloaded the data set from there. So now we have the URL of the data set, and we're going to go back to the command line. Now we have 2 adventures today, so let's just make a folder for each one. So we do make directory, and we move into the first adventure. Now we want to download the data. There's a command that allows us to do that, and it's called curl. And the syntax is basically as follows. You do curl and the URL of the file that you want to download. In the case of the NOAA, when you download data, they give you a URL that's only valid for a few hours or so. And so I put the data sets up on my website, so you can try this out afterwards if you want. Now we'll make one modification to the curl command. We'll put dash lowercase o data.csv. And what this says is go to the URL that's listed at the very end, download the file temp-orem.csv, and store it locally as the file data.csv. Okay? So we do that. It'll show you the progress, but this is a pretty small file, so it's almost instantaneous. And now we can actually verify that we've downloaded the file using a command we learned earlier called ls. So we type ls, and it tells us that there is indeed a file called data.csv. So now what we want to do is one of the first things that you always do when you're doing a data science project, which is you get the data from somewhere, and you want to know what it looks like, right? I mean, of course, this data is pretty small, so you could open it in Excel or in an editor, but for a large data set, this would be unfeasible. And so to preview the data, we can use a command called head, followed by the file name. And essentially what it will give us is the first few lines of that file. And the nice thing is, just by looking at the first few lines, we can deduce several things. First, the first column is a station ID, followed by the name of the station. This is going to be exactly the same for the whole file because I downloaded data just from that station. And then we have a column for the date. So every single day in the last 100 years. And for each day, we have the maximum temperature that was recorded and the minimum temperature that was recorded. It also has a t-obs column that basically tells you the temperature at the time of observation. The time of observation is not included in this data set because it's not useful for us today, but you can download these things from the NOAA. And so then, we, like good data scientists, we look at this and we start thinking, wait a minute, on April 1st, 1916, the highest temperature recorded was negative 9,999 degrees, which is a little strange. So we go back to the NOAA website, and this tells us that this is simply a placeholder to tell us that there was missing data for that day. We look again at this data, and we notice that the numbers are quite large. So here on April 9, 1916, it was 194 degrees. And no matter if you use Celsius or Fahrenheit, this is pretty hot. So we go back to the NOAA website again, and it turns out that these numbers are in tenths of Celsius. So 194 is really 19.4 degrees Celsius. So okay, now we've previewed the data. We've made sense of all the weird things that we see. Now what we want to do is sort this file by the column Tmax. And this will give us the dates that have the highest temperature. And Tmax column is column 1, 2, 3, 4. So we want to sort on the 4th column. As it turns out, there's a command called sort that allows you to do that. And the way it works is that you tell it which file you want to sort on. But just executing this command is not going to work. because by default, it will think that you want to sort on everything, on the whole line. But we just want to sort on the fourth column. So let's tell sort that. We do sort -k4, and the K stands for key, but you can think of it as a column. But it's not quite the column, because sort is expecting a range of columns to sort on. And so if you just give it the first column to sort on, it will start sorting on column 4 and keep sorting till the end of the line. And we don't want that. We just want to sort on the fourth column. So we tell it start at column 4 and end at column 4. So this means that we're just sorting on the fourth column and the fourth column only. However, this doesn't quite work on its own, because sort doesn't know that our file is comma delimited. Right? I mean, we can see that, but sort does not assume these things, so you have to tell it that actually my file is comma delimited, and you do that with a -t flag. So now we're saying, okay, sort the fourth column and just the fourth column, and by the way, my data is comma delimited. So two more things we have to do. First, the data that we're sorting are numbers, and by default, sort is going to sort numbers like 1, 10, 100, instead of 1, 2, 3. So we want to tell it we're sorting numerical data, so we use -n. Okay, we're almost there. Now sort by default will do sorting in ascending order. We want descending order because we want to see the hottest temperatures first. So we do -r to do reverse order. And when we -n is numeric. And so now we can see that the first few lines of this output indicate the top 6 hottest days around that area. And the hottest is July 13, 2002, with 42.2 degrees Celsius, which is about 108 Fahrenheit. And we can do a little more sanity checking like we did at the beginning. We see that the hottest temperatures all happen in July or August. So this is slightly reassuring because it makes sense. If we saw something like January, we'd be worried that something was wrong with our analysis. Yes?
So the header column there is strings. So does it put all the strings in?
Yes, I believe it does. Yeah. So we're basically done with our first adventure. And we were able to answer this question in one command line. Okay, now let's do the second adventure. We want to answer the question, how often are flights on time? And we can get this kind of information from the Department of Transportation, which keeps track of these things. And so I went on their website, and just as an example, I downloaded data for November 2014, got data for 14 carriers and 29 airports all across the US. And just so this analysis makes sense, keep in mind that the Department of Transportation considers a flight to be late only if it arrives late greater than 15 minutes to the gate. So if it arrives less than 15 minutes to the gate late, it is not late. Okay. So now let's analyze this data. Now we're back to our command line. We're in the Adventure 1 folder. So I showed you how to get into a folder, but let me now show you how to get out of one, because we want to go back to the analysis folder and create Adventure 2. And the change directory command will allow you to enter cd ... to go back to the parent folder. So ... just means parent folder, 1 ... means current folder. So no matter where you are in the file system, this will hold true. And now we'll make a directory for Adventure 2. And now we'll go into Adventure 2, but instead of just typing cd Adventure 2, because that's a lot of work, we can type cd adv and press tab. And the command line will autocomplete to as much as it is sure about. Because there's only 2 folders in there, Adventure 1 and Adventure 2, and then we can just type Adventure 2 and press enter. Now we want to get the data. So again, we can use curl. This time I just want to show you a variant of curl. Instead of -o in the name of the file we want to call it, we're going to call curl -o. and we don't specify a file name. And this just means go to this server, download the file delays.csv, and just save it as delays.csv because I don't want to rename it. So when you do that, you'll download it. And then, again, the first thing we want to do is preview the data. So we can use head. Unfortunately, when we do that, we get this whole slew of lines on the command, and it's hard to actually see what's going on because the first line actually spans 4 lines because of word wrap. So let me introduce another command that will allow us to get over that. And there's a command called less that allows you to navigate through a file up and down and right left. And if you do less -S, it will fix this problem we had with word wrap. So if we press enter, this is what it looks like. And now this looks absolutely beautiful. We can clearly see the columns. We have, for every line, we have a year, a month, we have a carrier, and we have an airport. So each line in this file gives us information about flights that happened for one airline at one particular airport and 1 month of the year. And we notice that there are useful columns for us, like ARR flights, which will tell us how many flights have arrived in that airport from that airline in that month. And if we scroll to the right, we can see more interesting columns, which will tell us how many delayed flights of more than 15 minutes happened at that airport for that airline. And we keep scrolling and we can see other things, which is the number of flights that were canceled or diverted. And so just to make it a fair analysis, we're going to consider canceled flights and diverted flights as being late, because that's what will end up happening. So now we can exit less using Q, and this is the formula we want to calculate from the data file we have. Let's just put it up there so we remember what it is. And if you remember, the late column was actually column 8. The canceled column was column 14. The number of diverted flights was column 15, and the total number of flights was column 7. So now what we want to do is go through that file, extract these columns, and just sum them all up. And to do that, I'm going to introduce another command that's essentially its own language called awk. And awk is a really useful command, and it allows you to execute a script on every line of a file. And so the syntax is as follows. On the very left, you have awk. On the very right, you have delays.csv. And in between a quote and the brace, you can enter a script that's going to be run on every line of the file delays.csv. And awk, a bit like sort, doesn't know what format of our file is, so we have to tell it that our file is comma delimited using -F. In sort, it was -T. And so this says, I'm going to launch awk, and the delimiter is a comma. And the file that I want to do this on is delays.csv. And the most basic command that you can actually run on each line of a file is simply to print that line, right? So if we press enter, we'll get every single line of the file. So that's not very useful, but it's a starting point for doing more complicated things. Instead of printing the whole line, we could print one column. So what if we wanted to output on each line just the 4th column? We can do that using the syntax $4, and dollar just represents the column. So here, for each line of the file delays.csv, we're going to output whatever's in the 4th column of that file. And if you press enter, you'll get just that 4th column, and it's a pretty long list of things that appear on the screen. Yes?
Is it capable of saying get at the last column? So I don't know how many columns I have.
Yes.
Always get the last one.
Yeah, so there are predefined variables in awk. So, for example, there are variables like nr that will tell you which line you're in the file. There are variables like, there is one to tell you how many columns there are, and I'm blanking on the name of it, but it definitely is there. And so for the last 2 commands, each time we run awk, we see the output for every line of a file. But if our file was gigabytes in size, that would be a pretty big waste of time. So what we want to do is really, can we run head on the output of awk? And the answer is yes, and there are two ways of doing that. One way is simply to run awk and to use the greater than symbol to basically send the output of awk to the file temp. And then it will not output anything to the screen, and we can do head temp. And it will show the first 10 lines, which is OK. But we still had to do this temporary file, which seems unnecessary. So I want to introduce this concept of piping, which is extremely important in Bash. And what it allows you to do is essentially send the output of one command to the input of another command. So here we want to send the output of the awk command to the input of head, and the pipe is denoted with a vertical line. And so here, basically it means go through the awk script and print out the first 10 lines of the output of awk. And this is great because we've saved, going to the hard drive and saving a file, which is much slower than just writing to memory. And so this is a very important pattern that you'll see a lot if you do command line programming. Okay, so now we have the fourth column, but we're more interested in the seventh column, so why don't we output that instead of the fourth? And if we do that, we'll see the first 10 lines of the number of flights that have arrived. So now we want to add up all these numbers. And awk allows you to do these things using the following syntax. We can define a variable called total. And total is going to be equal to the previous value of total, which it's going to start out as 0, plus the current value at the seventh column. And then if we press enter, nothing happens because we didn't use any print statements. Right? So the variable total within awk contains that total, but these variables are not available in Bash. And so what we want to do is use another feature of awk, which is the end block. And it looks like this. And basically it means once you finished running through the entire file, execute the following. And we just want to print the total. Okay? So now we're going through each line of delays.csv, adding up the number of total flights. And once we're done going through all the file, we output the total. And if we press enter, we get the total number of flights for November 2014, which is 462,054. So that corresponds at the top to our denominator. And now we want to do the same thing for our numerator. And it's exactly the same syntax. Instead of total, we can say define a variable called late. And late is equal to the previous value of late, plus add up the columns that define late flights, canceled flights, and diverted flights. And once you're done, you print out the value of late. And there are 89,665 flights that were late in November 2014. So we can replace that number at the top. And so doing that calculation tells us that 19.41% of flights are late, meaning that about 80.59% of flights arrived on time at the gate. And on time, it means less than 15 minutes late. The nice thing about this kind of analysis is that the Department of Transportation does this themselves, and you can verify that you did the right thing by going on their website. And in fact, we get the exact same number, which is really nice if you're starting out, because it means that you can verify that what you're doing makes sense. And that's basically it for the second adventure. So what's next? Well, the only advice I would give is if you're interested in learning more about Bash programming and command line, I would just encourage you to analyze your own data sets, either from your own company, from your own side projects, or even you can go to these two websites, which will have a huge repository of data. Data.gov will tell you about data from all government agencies. So today we talked about weather, we talked about Department of Transportation. There's tons of other data sets that are out there that you can use. Amazon also keeps a really long list of publicly available data sets that you can play around with. And another really useful tool is, other than your search engine, explainshell.com. When you go there, you can paste an entire command, and hovering over different parts of the command will tell you what they do. And so if you hover over the -t in sort, it will tell you what that does versus the -n. Finally, if you're interested in the kinds of adventures that we talked about today, I'm currently writing a book called Adventures of Data Science with Bash, where each chapter is an adventure like the one we've done. So, for example, we answer questions like, when people go to Chipotle, do they prefer steak burritos or chicken burritos? Or questions like, in New York City, what is a typical tip of a cab driver? And we answer all these questions just using publicly available data sets. So if you're interested, you can sign up to the mailing list at adventuresindatascience.com. So thanks for coming. That's all I had today. Questions, yeah?
How platform agnostic is it to, say, Ubuntu or OpenSUSE?
Yeah, most of the commands I've talked about today should work on every platform. So for example, I used curl to download data. Typically I use wget, but that doesn't work on Mac. But generally speaking, I try to make it as applicable as possible. Yep.
Is it possible to do the math in the awk command?
Yeah, it is. So you can actually just write one awk command that defines total and late, and using the end block, you output, late divided by total. Although I'm not too sure if it does floating points, so you might have to multiply by 100 at the front.
And then just figure it out later.
Yeah. Or there's another command called BC that does calculator. Yep.
So, I'm all about improving my command line food and whatnot.
Yeah.
Why do you like pursuing Bash to do data science stuff rather than like Python or R or something else like that?
Yeah, I mean, in reality, I use Python and R as well. But sometimes, I'm dealing with a large data set. I just want to do something really quick, like, reformat the file. Because, in science, there are probably like hundreds of formats and new ones are created every day. So sometimes it's as simple as changing the semicolon to a tab and things like that. In those cases, it's extremely powerful. But when you're doing statistical analyses, definitely Python and R are the best. Any other questions? Cool. Thanks for coming. So I have cards for this book in case you're interested. I can give it out.
Thank you so much.
Yeah, thanks.